Hey guys, it's David here, and we're going to be working with cyclohexane chairs today. So our question says, draw the two chair conformations of trans 1-ethyl 2-isopropyl cyclohexane and determine which conformation is the most stable. So the first thing we're going to do is go ahead and draw our chairs. I like to do it with drawing two parallel lines and then connecting them up here and one going down. So it's not the most artistic rendition, but it still kind of looks like a chair. Now, the first thing I do here is go ahead and number each carbon. I'm going to change color here. So this will be our first one, 2, 3, 4, 5, and 6, because each peak or corner is actually a carbon in the molecule. And the molecule is 1-ethyl, which means there's a ethyl group on the first carbon. I'm going to go ahead and draw it in the axial position. So an ethyl is 2 carbons, so CH2, CH3, connected at the carbon. And then for 2-isopropyl, I'm going to draw it on the second carbon. And since it's trans, it's going to be going in the opposite direction. So this one was pointed up. The isopropyl is going to be pointed down. So CH3, CH3, H. Now, there's also an axial group here, or equatorial group, sorry, here and here, which have hydrogens. And if it helps you to go ahead and draw through all the rest of them, just so you're not confused, where's axial, where's equatorial. Axials are the ones that are pointed either straight up or straight down in line with the axis, and the equatorial ones are kind of a little bit tilted, and they rotate every single carbon. So on carbon 2, this axial one was down, so it's going to be up here. The equatorial is going to be down. Axial is going to be down here. Equatorial up. Equatorial down. Axial up, axial down, equatorial up. Now you can't just leave it like that, because that's actually representing a methyl group, so you can just go ahead, every one of these carbons has 2 hydrogens coming off them, so fill it in with a hydrogen. Okay, so that's our first chair. Now it wants us to see if there's any other conformations of this that might be more stable. So what I like to do is go ahead and do a chair flip, and when I do that, we're gonna flip it so it's facing the other way. Now I bring this corner here down and this corner up like this, and this is where the numbering is important, because it helps you keep track of what went where. So I'm gonna go ahead and draw the new chair same way, but this time flipped. Okay, and as I said, this number is now on this corner. So this is the new number 1, and then you just go in along the same direction following the numbers. So this is the new 2, 3, 4, 5, 6. Now it's the same molecule, so the same stuff is attached to the same carbons. And when we do a flip, we keep the direction that it was in, not whether or not it was axial or equatorial. The axial equatorial thing stays, so the axial stays here, here, and it rotates every time. And in this chair conformation, the ethyl on the first group was pointed up. So we're going to keep it up, and it's actually going to be on an equatorial position now. Go ahead and fill in that hydrogen. You can do that here just so we don't lose points. And so now on the second carbon, there was an isopropyl that was going down. And remember I said this axial is down, so this axial is up. So you're saying, I know the isopropyl needs to be down. Is it axial or equatorial? It's going to be axial in this case, because it's still down. CH3, CH3, H. Okay, and don't forget this is a hydrogen. And then just for completion, and so it makes sense, go ahead and draw all these hydrogens in. These are all hydrogens. Okay, and now on to the last part of the question is which one is more stable. as a general rule of thumb, you want the groups of interest, in this case of isopropyl and an ethyl group, you want them to not be axial. So at a quick first glance, you can say, oh, this conformation has 2 axial, this one has no groups of interest axial. So the short answer is this is more stable. And the reason for that is because when you have groups axial, there's what's called diaxial interactions. They're going to interact with each other, so all the axial up ones going to interact with all the axial up ones. Axial down with those. Oh, looks like I forgot a hydrogen there. So there's a lot of interaction going on here within the molecule that makes it not energetically favorable or stable. So that is why that one is more stable. And that's it. I hope you guys found this helpful.